All right, so we were looking at molarities, and the next thing we're going to look at is molarity by dilution. So now what we can do is take a solution of higher concentration, add more solvent. That increases the amount of solvent, which will then lower the concentration. So we're going to take a small volume of a concentrated solution, we're going to add solvent, we're going to have a larger volume now of a dilute solution. Now, the amount of moles doesn't change throughout this process. They're going to remain the same. So the only thing that's changing then is the volume, which is what's going to drive that concentration to go down. So diluting solutions then, moles of solute do not change upon the dilution. We're simply changing the volume. That means the number of moles in the dilute will equal the number of moles in the concentrated. So the volume of the dilute solution times the dilute molarity would equal the volume of the concentrated solution times the concentrated molarity. Okay, so moles of solute in the dilute solution, moles of solute in the concentrated solution. This is represented by M1V1 is equal to M2V2. Here they've just reversed those two. We have the volume times molarity equals volume times molarity. Our dilution equation will work for any type of concentration though. So while in chemistry we typically work with molarity, you could work with percent solutions and the same formula will work. And we refer to it as M1V1 is equal to M2V2. So learning check for dilutions. What volume in milliliters of 16 molar H2SO4 must be used to prepare 1 liter of 2 molar H2SO4? All right, so we're going to start by taking our volume times our concentration. We just have to make sure we get them paired up right. Which one we let be V1 and M1 doesn't really matter as long as they're paired correctly. So what volume, so we're going to let that be V2 of 16 molar. So V2, 16 molar, this is going to be M2. Must be used to prepare 1 liter, we'll let that be V1, of 2 molar H2SO4. I'll let that be M2. So we're going to take 1 liter times 2 moles, 2 molar. That's going to equal my volume, my V2, times my 16 molar. So rearranging then, my V2 would equal 1 liter times 2 molar divided by 16 molar, which would be 2 over 16, which is going to equal 0.125 liters times 1,000 milliliters per liter, gives me 125 milliliters. All right, so hopefully that makes sense. We will need 125 milliliters of 16 molar H2SO4 to make 1 liter of 2 molar H2SO4. Right? Now, preparing solutions of known molarity, again, very much like we saw with the solids, what we'll do is we'll use our volumetric glassware. So we'll use a pipette here. Typically, these are not glass any longer. Now we have micro pipetters or automatic pipetters. So it'll be a push button. Here they're just showing you can use a bulb and then pinch the bulb off by putting your thumb or your forefinger on top, creating a vacuum. So that's going to hold your solution in here. Typically, not really showing a very good volumetric pipetter either. Here, there's a line usually, like we saw in that volumetric glassware, right? So here on the volumetric flask, we have that line again. On the pipette, it'd be the same way. And so you'll pull the liquid up to that line, then you'll pull this off, put your finger on top. And a lot of times what you'll do is you'll pull past that line. So we'll pull the solution up to like in this area. That way we have time to take the bulb off, put our finger on. Then we can slowly remove our finger to allow that volume to come down, to trickle all that out. Then we'll move it over to the flask, put it in the flask just like we did with the solid, right? Then backfill that with water to get to the concentration we're after. So we'll use a volumetric pipette to transfer the stock solution and then use a volumetric flask to receive the final solution. Mathematically though, we don't worry about those details, right? So mathematically, what volume of 12.1 molar HCl is needed to create 250 milliliters of a 3.2 molar HCl solution? All right, hopefully you got A. And the way you might have done that is take 250 milliliters times 3.2 molar is equal to whatever volume it is you're looking for times 12.1 molar. Rearranging, of course, will give us 66 milliliters. Now, as far as your concentrations go, we've been working with liters as our volume. all the way through because this is moles per liter. But here, notice we went ahead and did this math with the milliliters. What you're going to do is just keep track of your units. And so if I have milliliters in the beginning, then I need to have milliliters in the end. It will work for this. It doesn't matter. Now, that's not always true. We'll see in gas laws when it comes to temperatures, we can't just willy-nilly it and just throw whatever units we want in there. Things have to be done a right way with units. But for these, as long as you're letting your milliliters work through, letting your molarities cancel out, or your percents, because you could do percent solution, letting those cancel out, all of that works out to be the same. All right. So a 25 milliliter of 6 molar HCl is diluted to 500 milliliters with water. What is the molarity of the resulting solution? So again, we'll do multiple choice here. And hopefully you've got E. And the way we would have done that, 500 milliliters times my new concentration is equal to 25 milliliters times 6 molar. Rearranging and solving, we get 0.30 molar. All right. So now what we're going to do is take this chapter, combine it with chapter 3, and look at solution stoichiometry. Now I've already pointed out that it's going to be a 3-step process, just like we saw before. So it often works with solutions when conducting reactions. How do we determine amounts needed to completely react one compound? Just like any other stoichiometry problem, except now we're going to use our volume and molarity to obtain moles of each substance. So again, if you think about it as being in those 3 steps, before we used our mass and our periodic table to figure out the first step and the last step. Now what we can do is introduce a solution, and so the solution will allow us to use the volume and molarity either in the beginning or the end or both to do solution stoichiometry. All right, so your general scheme then, you'll have your volume of your reactant. We'll calculate the reactant molarity, so we'll have moles of reactant. Then we'll use our mole to mole ratio, just like we did before. That'll give us moles of product. So that's the middle step. The middle step is always a mole to mole relationship. Then we'll use the product molarity to figure out the volume of the product. So again, we can substitute in this step or this step for mass. So it's just pointing out that we started out with mass to mass relationships, but we don't always start with a mass, right? Sometimes we already pointed out it won't react if it's just 2 solids. If I take 2 solids and put them together, nothing happens. But if I put water in, all of a sudden, now we can get a reaction to happen. So we need to be able to work from both the liquid and solid state. And of course, we'll introduce gases later on in life, and we'll see that we can work the same type of math with the gases. So, solution stoichiometry problem. How many milliliters of 0.0475 molar H3PO4 could be completely neutralized by 45 milliliters of 0.1 molar KOH? And of course, the balanced equation for the reaction is this. Now remember, test day, you'll probably have to balance that reaction yourself as well as know the names instead of these formulas. So here we're going to take H3PO4, we're going to add 3 equivalents of KOH to neutralize it. That's going to give us K3PO4 and 3 waters. So again, the strategy, we're going to take the KOH solution, get to the moles of KOH. We'll use our balanced chemical reaction, get from moles of KOH to moles of H3PO4, and then finally calculate our molarity or volume, whatever it's asking for. It says how many milliliters, so we'll be looking for the volume of H3PO4. So calculate moles of KOH. We'll take 45 milliliters of KOH, convert that to liters, multiply that by the molarity. Everything will cancel out to give us moles of KOH. Then, of course, we'll go from moles of KOH to moles of H3PO4. We'll use our balanced chemical reaction for that. So then we'll do that times 1 mole of H3PO4 for every 3 moles of KOH we'll require. Moles will cancel out, and now we have moles of H3PO4. And then finally, our third step, which used to be the periodic table, will now be calculate the volume of H3PO4 needed by simply using the molarity they gave us times the amount of moles we just calculated. Of course, we'll divide by the molarity because we're going to multiply by the liters to get rid of the mole and give us milliliters. And here we need 31.6 milliliters of H3PO4. All right, so stoichiometry of ionic equations. Sometimes we need to know concentrations of ions. This is important for the net ionic reaction stoichiometry. So molar concentration of a particular ion equals molar concentration of salt multiplied by the number of ions of that kind in 1 formula unit of salt. What? So what they're saying is this. If I have Na3 PO4 and I've got this balanced reaction so that it works out that I need 2 of these, then what this is telling us is when we break this apart and we know the concentration of this, it's going to be 2 times 3 for that. So we're going to get 6 Na pluses, right? And 2 PO4 minuses, 3 minus, right? Now if our concentration here was 2 molar, right, 2 moles per liter, and let's just say I've got 1 liter to keep it nice and easy. Well, if I have 1 liter, then I'm going to have 2 molar, so I'm going to have 12 moles of sodium in there and 4 moles of phosphate. That's all they're saying about that. Okay, long way to say something simple. All right, if you have 0.150 molar Na2CO3, what is the concentration of each type of ion in solution? Okay, so that means if I have Na2CO3, it's going to break apart into 2Na plus CO3 minus. So let's calculate the concentration of the Na ions. So sodium ions then. Well, we have a 0.15 molar solution per liter. In that we have 2 moles of Na for every 1 mole of this, which means then it's 0.3 molar Na plus. Okay, we can see the moles of sodium carbonate cancel out. We can do the same thing for the carbonate, except that second step is going to be 1-to-1. The moles of sodium carbonate will cancel out, and we'll be left with 0.150 molar CO3 2 minus. So hopefully that's pretty straightforward. All right. If the solution concentration of sulfate ion is 0.75 molar, what is the concentration of aluminum sulfate, assuming that all of the sulfate ion comes from the aluminum sulfate? Of course, it's multiple choice. So if the solution concentration of sulfate ion is 0.75, assuming that all the sulfate ion comes from aluminum sulfate, what is the concentration of aluminum sulfate? And hopefully you got C here. And the way we would have done that is we're going to take 0.750 molar sulfate times 1 mole of aluminum sulfate for every 3 moles of sulfate. So we're going to divide by the 3 moles. Moles of sulfate will cancel out, and we'll be left with 0.250 molar aluminum sulfate. All right. Net ionic equations and solution stoichiometry calculations. So what volume in milliliters of 0.5 molar KOH is needed to react completely with 60 milliliters of 0.250 molar FeCl2 to form the iron 2 solid? All right, so we're going to write our balanced net ionic equation first. So you might need to write out the whole equation to do that. So we're going to have KOH, right, plus FeCl2. And so that's going to form KCl plus the iron hydroxide solid. So potassium ion should cancel out on both sides. Chloride ion should cancel out on both sides. And so we're going to be left with Fe2 plus 2OH minus produces FeOH2. All right, so in our minds, typically we'll figure out what the game plan is going to be here. So they want to know what volume of 0.5 molar KOH is needed to completely react with the 0.25 molar FeCl2 to form the iron hydroxide solid. So we're going to start with the concentration of the FeCl2 because we want to react all of that. So we'll figure out moles of FeCl2, which will give us moles of iron to moles of OH minus, which will give us volume of OH minus, which will give us the volume of KOH. So convert molarity of iron chloride to molarity of iron to moles of iron. So we're going to take 0.250 molar FeCl2 It's 1:1. So for every 1 mole of iron chloride, we get 1 mole of iron. And then we're going to multiply that by 60 milliliters because that's how much we have. And that's going to give us 0.0150 moles of Fe2+. Now that we have moles of Fe2+, we're going to use that to figure out moles of hydroxide. From that, we're going to get the formula, right? So we'll use the formula. We know it's iron 2 hydroxide, so it's going to be 2 hydroxides for every 1 iron. So we just figured out we needed 0.0150 moles of iron. We'll need 2 times the amount of hydroxide, which gives us 0.03 molar hydroxide. Now we're going to take hydroxide, turn it into volume of hydroxide, which will give us the volume of the KOH. So for 0.03 moles of hydroxide, for every 1 liter of hydroxide, it was half a molar, right? So 0.5 moles for every 1 liter. My liters will cancel out. For every, the moles will cancel out. And then for every 1 liter of hydroxide solution, it'll be 1 mole of hydroxide will give me 1 mole of KOH. Then I can convert finally my liters to milliliters, and I get 60.0 milliliters of KOH. All right. How many grams of lead iodide will form if 20 milliliters of 0.8 molar iron 3 iodide, is mixed with 50 milliliters of 0.3 molar lead nitrate? So we have lead nitrate plus 2 iron iodide going to 3 lead iodide plus iron nitrate. So the first thing we'll need is our net ionic equation. So the lead nitrate will break apart into its pieces. Iron iodide will break apart into its pieces. Lead iodide is going to precipitate out, and then iron nitrate will be left in solution. So the iron will be on both sides, it'll cancel out. The nitrate will be on both sides, it also will cancel out. So that our net ionic equation then would be lead 2 plus 2 iodides will produce lead 2 iodide. All right, the strategy, much like before, we're going to take our volume of our lead nitrate, figure out moles of lead nitrate. Moles of lead nitrate to moles of lead to moles of lead iodide to grams of lead iodide. We'll take our volume of iron iodide to moles of iron iodide to moles of moles of iodide to moles of lead iodide to grams of lead iodide. So very similar to what we did last chapter, except now we'll have some extra steps of solution calculations going on. The calculation that gives the least PbI2 determines how much is formed and which reagent is limiting. So starting with the lead nitrate then, we'll take 50 milliliters of lead nitrate, convert that to liters. That way we can get the liters to cancel out with the molarity. So we're basically going to take our volume times our molarity. We'll then cancel the moles out to get moles of lead. It's 1:1, which is going to be true for the product. And then, of course, moles of product to grams of product. That says we're going to make 6.92 grams of product. Next, we'll look at the lead iodide, go through the same process. We have 20 milliliters of the lead iodide. We'll convert that to liters, so that we can multiply that by our molarity. That's going to produce 3 moles of iodide for every 1 mole. And then for every 2 moles of iodide, we'll make 1 mole of lead iodide. Multiplied by the molar formula gives us 11.06 grams. So which one's our limiting reagent? Well, here we made the least amount, which means the lead nitrate will be our limiting reagent. So since lead nitrate is the limiting, and only this much product can be made, right? All right, quantitative analysis. What substances are present in a sample? Quantitative analysis is going to be how much. Measure the amounts of various substances in the sample. Convert all of an element present in a sample into a substance of known formula. Then use the amount of this known to determine amount of the element present in the original sample, the unknown or the analyte. So, a 1 gram sample of insecticide is decomposed so that all the chlorine is converted to chloride. Silver nitrate is added to precipitate all the chloride as silver chloride. The solid, after filtering and drying, is found to weigh 2.022 grams. What is the percentage by mass of the chloride in the insecticide? All right, a lot of information in this question, right? So they've told us how much sample we have to start with. Then we're going to decompose all of that to basically get to the chloride. Now remember, that's all going to be in solution. Then we're going to add silver until we can get all of it to turn to silver chloride. Then we're going to dry that product out and we find out how much product we actually made. Then what we want to know is, what is the percentage by mass? Okay, so we're going to take the mass of silver chloride, we're going to turn that back into moles of silver chloride. That's going to tell us how many moles of chlorine, which is going to tell us the mass of the chlorine. We'll have the mass of the chlorine, we know the mass of the sample, we can figure out the percentage. So how much chloride then is in 2.022 grams of silver chloride? We're going to start with 2.022 grams. We're going to go to our handy dandy periodic table. We find out that's 143.3 grams for each mole. So now we'll be in moles of silver chloride. For every 1 mole of silver chloride, we produce 1 mole of chloride. Silver chloride moles will cancel out. Then we'll go back to our handy dandy periodic table. It's 35.45 grams of chlorine for every mole of chlorine. So that tells us that we have 0.5002 grams of chloride. Remember that the question was how much chloride percentage in the original sample. So we'll do mass of chlorine over mass of sample. So we're going to take 0.5002 grams, divide by 1, times 100%, and we get 50.02% chloride. All right, your turn. All right, so hopefully you paused the video. You went ahead and gave this problem a try, and now let's see how it's going to work out. The first thing you're going to want to do is write the balanced chemical equation. Then you're going to take the moles of HCl, the molarity of the HCl, convert it to moles of HCl, to moles of sodium carbonate, to mass of sodium carbonate. So a 4 gram sample that contains sodium carbonate and an inert soluble salt is dissolved in 100 grams of water. Hydrochloric acid is added to react with the carbonate ions. If 33.5 milliliters of this HCl was required to just completely react with all of the sodium carbonate, what was the mass percent of sodium carbonate in the original sample? All right, so you've got a strategy now. I'm going to give you another long pause here. All right, so just in case you weren't able to get started, then you just needed some strategy. Now let's see. A 4 gram sample that contains sodium carbonate and an inert soluble salt works out to be what percentage? And hopefully you got 23.3%. Now, how did we get that? First, you'll write your balanced chemical equation. Sodium carbonate plus 2HCl goes to sodium chloride plus CO2 gas plus the H2O. So there's our balanced chemical equation. Now our first step, moles of HCl, molarity of HCl to moles of HCl. Second step, moles of HCl to moles of sodium carbonate. Final step, moles of sodium carbonate to grams of sodium carbonate. So we have 33.5 times 10 to the negative 3 liters of HCl, right? So in other words, we had 0.0335 milliliters, right? Times 0.525 moles of HCl. Liters of HCl will cancel out. We now have moles of HCl. So molarity of HCl to moles of HCl completed. Now we'll look at moles of HCl to moles of sodium carbonate. According to our balanced chemical reaction, 1.76 times 10 to the negative 2 moles of HCl times 1 mole of sodium carbonate for every 2 moles of HCl that we use. Moles of HCl will cancel out, and we'll have 8.80 times 10 to the negative 3 moles of sodium carbonate. All right, last step. 8.80 times 10 to the negative 3 moles of sodium carbonate to 106 grams for every mole. That means we have 0.933 grams of Na2CO3. Now, that wasn't the question. The question was, what's the percentage of sodium carbonate in the original sample? So, we know the mass of sodium carbonate. We know the mass of the original sample was 4 grams. So 0.933 grams divided by 4 times 100% tells us it's 23.3% sodium carbonate. All right, so the segment went a little long. We do have one more topic to talk about. I really didn't want to make it 9 segments altogether, but apparently it's going to take that because I really don't want to go past 20 minutes, let alone go longer than 25. So the last thing we'll talk about is titrations, which is just another way to look at molarity and stoichiometry in general. All right, so stay tuned for that last segment.